Okay, folks, so here we are with our 40th installment for the MLOs for this unit. And what we're talking about now is still dispersion, measures of dispersion. We're talking about standard deviation specifically, which we saw in our last section, and we're going to talk about range. So those two things and how we kind of use those to sort of analyze a data set and talk about how spread out the data set are. So we're talking about range and standard deviation. All right, so here we go. First question, so just a couple of examples. We're doing some practical things here. It says data set number 1 has a standard deviation of 8.3. So notice this little funny looking symbol that we use here for standard deviation. Where am I? There we are. So we get this little thing right here. This funny little thing is like a circle with a line coming out of the top. That's called a sigma. It's a Greek letter sigma. And that's what we use to represent standard deviation. And it says that's 8.3. And it says the second data set has a standard deviation, or a sigma, 2. That's equal to 3.2. Okay. It says which statement about the two data sets is most accurate? It says the data in set 1 are larger on average. If all the numbers were bigger, that would mean they'd be bigger on average, so they have a bigger average, but not necessarily, they wouldn't necessarily be dispersed as much. It says the data in set number 1 for B. So I'm going to say no to A, and then for B it says the data in set number 1 are smaller on average. Well, that's the same thing, just sort of opposite. I don't think that's it. Part C, the data in set number 1 are more spread out than those in data set number 2. Yeah, that's probably what we're looking for. So remember, the standard deviation represents their average distance you are away from the mean. So a bigger standard deviation means on average the data values are spread out more away from the mean. So we're going to say data set number 1 is more spread out if sigma 1 is bigger than sigma 2. So that's what we're after. And then part D is going to be a no-no. It's just the opposite. It says they're more bunched together, which would be the opposite of being spread out, wouldn't it? So definitely C there. All right. In example 2, they're asking us to calculate the standard deviation of the given data set using the table shown. Okay, so there's only 4 values in this table set, or in this data set, and typically we don't ask students to do a standard deviation calculation because there's a fair bit to that formula. We don't ask you to do much of that with a big data set. So 4 values is really reasonable, I think. You could be asked to use your graphing calculator if your teacher wants you to use that, or spreadsheet or something, because technology is supposed to be part of the course. So your teacher could ask you to do it that way, but we don't require that we do it with a big data set. So it says x bar is equal to 8. So all they did there was they took the average. 7 and 8 is 15, plus 12 is 27, plus 5 is 32. Divide that by 4, and they got an average of 8. Okay, so there's our mean. The next thing we want to do is we want to take all the x values. Now remember, all the data values are called the x's, and we want to subtract the mean from each one. So let's see. 7 subtract 8 would be -1. 8 subtract 8 would be 0. 12 minus 8 would be 4. And 5 minus 8 would be -3. Okay, so that was pretty good. Then the next thing we do is we take those differences that we just found over here, and we square them all. Okay, so -1 squared is 1. 0 squared is 0. 4 squared is 16. -3 squared is 9. Okay, and then down here, it says we want to take all those squared distances. That's supposed to be an 8, not a 10. How silly. So we're going to take all those squared distances, and this little funny thing out in front, that's a capital letter sigma from the Greek alphabet. But what that means is add them all together. That's an abbreviation for sum. So what's the sum of all these? 1 plus 0 plus 16 is 17, plus 9, I think, is probably 26. Okay? So then to actually find out what our standard deviation small sigma is, we take the square root of that sum, which was 26, and we divide by n, which was the total number of data values that we had. So this is the number of data values. Oh, data, excuse me, values that we had. And that in this case was 4. So all I have to do is I have to ask my magic calculator, what's the square root of 26 divided by 4? So 26 divided by 4, then square root is about 2.55. So what that tells me is that down here, I have a standard deviation of about 2.55. So on average, any random data value that I picked from this set of 4 would be about 2.55 units away from the mean. Okay? So remember, dispersion is the degree to which it's spread out. We could use range as a simple measure, but all that does is tell us the distance between the extremes. Standard deviation is much more effective, but the formula is a little complicated. We've been through it a couple times. Hope that helps.